In this lecture, I'm going to explain a really important concept for vector spaces, the concept of inner product. So far, we have defined what a vector space is by using the axioms. However, we have not defined how to measure distances and angles in an abstract way. For this, we need to introduce a way of measuring in vector spaces. This is done by introducing a new operation, different to the usual addition and multiplication by a scalar. This new operation acts on any two vectors, and the result is a scalar. It is called the inner product, and it is denoted with angle brackets as UV. We will study its axioms later, so that we can apply it to any vector space. But before looking into abstract axioms, it is best if we understand intuitively what it really is. In our rudimentary three-dimensional real space, the inner product between two vectors, u, v, is simply the well-known dot product, our old friend. The dot product acts on two vectors and gives us a scalar. So, for the moment, think about the inner product as being identical to the dot product, but keep in mind that we will later see that it is really more general. Let's look at a very important list of things that we can do with the help of the inner product. This is a long list and every item is very important, so let's look at them individually. The first item is the norm of a vector. Norm is simply the word that we use to generalize the concept of length to more abstract n-dimensional vectors. Similar to what happened with the dot product, the norm of a vector squared is simply the inner product of a vector with itself. Next, let's look at the concept of orthogonality between vectors. Two vectors u and v are orthogonal if and only if the inner product between them is 0. This is exactly identical to what happened in three-dimensional space when the dot product of two vectors is 0. Using this concept of orthogonality, we can now define an orthogonal basis. A vector basis made of the basis vectors e1, e2, all the way up to en is orthogonal when all the vectors are orthogonal to each other. That is, the inner product between any pair of two vectors is 0. We can further define an orthonormal basis. This is a basis of basis vectors e1, e2, all the way up to en, which are orthogonal to each other, and they are also unit vectors, which means that they all have a norm of 1. For example, the usual basis that we use in 3D space, x hat, y hat, z hat, is an orthonormal basis. This is very easy to see because all of these three unit vectors are orthogonal to each other, and the three are unit vectors with a norm of 1. This can be written mathematically by saying that the inner product between any two ei and ej vectors is equal to 0 if I is different to j. That is, if we are doing the inner product between two different vectors in the basis, they are orthogonal and therefore the result of the inner product is 0. But if we are doing the inner product of a vector with itself, then the result is the norm square, which is 1 because they are all unit vectors. This situation, in which something is 0 if I is different to j, and it is 1 if I equal to j, appears a lot in physics and mathematics. And we have a symbol for this. This is called the Kronecker delta, and is written as delta subscript ij. So this symbol gets a value of 0 when I and j are different, and gets a value of 1 when I and j are equal. When we are working with a vector space, it's always better to use an orthonormal basis, or at least an orthogonal basis. The reason for this is that it makes things easy and simple, and many operations are much easier to do if we are working in an orthonormal basis. Let's see two examples of this. The first example is how to find the components of a vector in a certain basis. Imagine you have a vector v. For the sake of this example, let's suppose this vector is given by 2x hat plus 4y hat. We know that this vector can be written in component form as v equals 2, 4 in the basis x hat, y hat. Now, we want to work in another basis, e1, e2. This would be very difficult, but we are lucky, because this happens to be an orthonormal basis. The two vectors, e1 and e2, are orthogonal to each other, and they both have unit length. In this example, they are given by e1 equals x hat plus y hat over square root of 2, and e2 equals minus x hat plus y hat over square root of 2. Check for yourself that this basis is orthonormal. Suppose we now want to find the components of vector v in the basis e1, e2. These are the coefficients of the basis vectors, which we may call v1 and v2. With these coefficients, we can write the vector in component form in the new basis. Thanks to the fact that the basis e1 and e2 is orthonormal, it is very easy to get the coefficients. We only need to do the inner product of v with each of the basis vectors to find the corresponding component. For example, the first component, v1, is equal to the inner product between the vector v and the basis vector e1. That's it. Since we are in real geometrical space, the inner product is the dot product. So if we do this dot product, we arrive at v1 equals 6 over square root of 2, which is our first component. The second component of the vector v, which we have called v2, is equal to the inner product between the vector v and the basis vector e2. If we do this calculation using the dot product, we find that v2 equals 2 over square root of 2. Indeed, those are the two components of this vector. This recipe is very easy to understand intuitively, because the components are simply the projection of the vector v into each of the orthonormal basis vectors. However, do not be fooled by the apparent universality of this argument. This recipe does not work if the vectors in the basis are not orthogonal to each other, because then the required components are not simply the projection. Finding the coefficients in this case becomes much more challenging, requiring the solution of a system of equations. That's why we always prefer to work with orthonormal bases. So we can add this simple recipe into our list. Although we have seen an example in a simple two-dimensional case, I really want to show you a formal mathematical proof of this recipe working in the general n-dimensional case, because it is very elegant. Let's say we have a vector written in terms of an orthonormal basis, v equals v1 e1 plus v2 e2, all the way up to vn en. Crucially, the coefficients v1, v2 up to vn are unknown to us. They are precisely the thing that we want to find. The recipe to find any of them is to do the inner product between vector v and the corresponding basis unit vector. For example, let's say we are interested in the ith component. Following the recipe, to get the ith component of the vector, we do the inner product with the ith basis vector, ei. So we substitute. Now, the inner product, like the dot product, is a linear operator, which means that we can apply it separately to each term in the sum. And again, due to the linearity of the operator, the scaling coefficients will simply scale the result of the inner product, so we can take them out of each term. And now we use the fact that the EIs are an orthonormal basis, such that the inner product between any pair of them is always 0. This makes all of the terms 0, except this single term in which the inner product is of the basis vector with itself, whose result is 1 because they are all unit vectors. This leaves us with the desired result, that the inner product of v with a basis vector ei gives us the component vi, which we were initially looking for. Remember, this is only true if the basis is orthonormal. Now, I keep writing the proofs using long notation, which means you are not getting trained to follow the usual textbook summation notation. So let me redo this identical proof in summation notation. This time I will not speak over it. You can follow it calmly, and if in doubt, you can check each step with the corresponding step in the fleshed out notation. This is clearly a much more concise way of working, and also provides a very nice example of how to deal with Kronecker deltas inside summation symbols. So now we have seen both a visual example and a formal proof for this recipe for obtaining the vector coefficients from any orthonormal basis. There is a very similar recipe for the case in which the basis is orthogonal, but not orthonormal. In other words, the basis vectors are orthogonal to each other, but not necessarily of unit length. In this case, we just need to add a division by the squared norm of the corresponding basis vector. The proof of this is straightforward, and almost identical to the previous one. Here it is for reference. Pause the video and make sure you can understand this proof. This is the way in which this would be proven in mathematical textbooks. It is also simple to understand this recipe intuitively, if you think in terms of the geometrical meaning of dot products. Give it a chance. Now, let's move to the last item in our list of useful things that we can do with the inner product. Projection of a vector into a subspace. The inner product gives us a nice way to find the projection of a vector into a subspace, and it is very, very useful. So let's do an example in three-dimensional space. Consider all of space, which we denote as V3D. Now consider a subspace. For example, let's take the two-dimensional xy plane, which we can label as W, and which we can define as the span of x hat and y hat. This is clearly a subspace of V3D. Remember that any subspace is a vector space itself, and therefore we can talk about this vector space W in terms of having an orthonormal basis, which in this case could be the basis x hat, y hat. Any vector V in 3D space has a certain projection into this subspace. This projection is defined as the vector W, which is inside the subspace capital W, and which is closest to the vector V. By closest, we mean that the distance, or norm, of the vector V minus W is minimized. For the sake of the example, let's say that V equals 2x hat plus 6y hat plus 5z hat. In this specific case, it's easy to see almost immediately that the projection is easily obtained by keeping only the x hat and y hat components of this vector. So W would be equal to 2x hat plus 6y hat, with no z component. This can be written as follows. W equals inner product of V and x hat in the x hat direction plus inner product of V and y hat in the y hat direction. This way of projecting a vector into a subspace can be applied to more general cases. For instance, consider a subspace plane written in terms of two basis vectors that are orthonormal, E1 hat and E2 hat. Now consider any vector V in the general 3D space. This vector will have a projection into the plane, which we call W. This projection vector W is given by moving along the E1 direction by an amount equal to the inner product between V and E1, and then moving along the E2 direction by an amount given by the inner product between V and E2. Writing this explicitly, we have that W equals VE1 in the direction E1 plus VE2 in the direction E2. As you can see, this is extremely simple, and it works thanks to the fact that the vectors E1 and E2 are orthonormal. So the general recipe in an n-dimensional space can be formally written as follows. Consider a space capital V. Now consider a subspace capital W, which is spanned by an orthonormal basis with basis vectors e1 hat, e2 hat, all the way up to en hat. Imagine a vector V living in space capital V and a vector W living in space capital W. The vector W, which is as close as possible to V, is given by this equation. W equals inner product of V with E1 in the direction E1 plus all the way up to the inner product of V with the unit vector En in the direction En. In other words, we move in the direction of each unit vector of the basis by an amount given by the inner product of V with the corresponding unit vector. And that's it, we finished our list. These are the type of things that the definition of an inner product allows us to do. So, why all the fuss about the inner product? Haven't we simply given another name to the dot product? The truth is that the dot product is just a particular example of a possible inner product. In other words, the inner product is a generalization of the dot product. The same way that vectors could be generalized to include interesting n-dimensional things, the inner product can be generalized into interesting things. Let's have a look at the Wikipedia entry for the inner product. An inner product space is a vector space with an additional structure called an inner product. This additional structure associates each pair of vectors in the space with a scalar quantity, known as the inner product of the vectors. Inner products allow the rigorous introduction of intuitive geometrical notions, such as the length of a vector. Okay, so the inner product is like an additional foundation that we add to the formal axioms of vector spaces. We add these new axioms and they enable us to extend our building even further. These are the axioms that the inner product must fulfill. Linearity in addition. So when one of the vectors in the product is an addition of two vectors, we can simply add the inner products. Linearity in scaling. When we multiply one of the vectors by a scalar, we can simply scale the inner product of the unscaled vector. And to be honest, I would like to join these two axioms into a single generalized linear axiom, which can look like this. When one of the vectors is a linear combination of vectors, we can instead do the linear combination of the individual inner products, and we get the same result. Next, the symmetry axiom. So this guarantees that the inner product of two vectors is independent of the order we choose. And finally, the positive definiteness axiom, where the inner product of a vector with itself is always positive, and is only zero if the vector itself is zero. Since this slide summarizes the main axioms of the inner product, I thought it was convenient to add here the definitions that the inner product introduces. The norm of a vector and the orthogonality of two vectors. We have already seen both earlier. But just to emphasize a subtle point, it's not that we need to be careful defining the inner product so that it gives zero when the vectors are orthogonal. No. Instead, it's the other way around. The definition of the inner product is what determines whether two vectors are orthogonal or not. In other words, the concept of orthogonality is defined from the inner product. Okay, so at this point you might be thinking, come on Paco, show us an example of an inner product that is not the dot product. So here comes an easy one. What happens if our vectors have complex numbers as their coefficients? This is very common in physics. For example, imagine the vector v equals 1x hat plus I y hat. So the x component is equal to 1 and the y component is equal to I, the imaginary unit. In this case, if we apply the usual dot product, we get weird results. Let's try to calculate the norm of v using the dot product. Norm of v is the square root of v dot v. So we do this, and we get it's equal to 0. Okay, we're getting a length of 0, for a vector that is not 0. The dot product is really not working well for complex vectors. Let's do another example. Vector A equals 1 plus I x hat plus I y hat. If we use the dot product to calculate the length of A, we get square root of minus 1 plus 2i. This is clearly a complex number. How can the length of a vector be complex? The dot product definitely gives ugly results. The traditional dot product is in fact breaking some of our axioms when we use complex vectors. We need a new inner product to work with complex vectors. We would like the norm of a vector to always be a real number, right? We would like the length of all vectors to be some real number. So the inner product of A with A should always give a real result. This can also be written by saying that the inner product of A with A should be equal to its own complex conjugate. In fact, this suggests that we should introduce a small modification to one of our axioms. Instead of demanding symmetry, we can demand conjugate symmetry. So if we swap the places of the two vectors, we get the conjugate of the result. With this version of the axiom, the inner product of vectors with themselves will be equal to their own conjugate, which means that they will be a real number. When we have conjugate symmetry, we must now be a bit careful with the linearity axiom. Because now, if we make a linear combination in the second vector of the inner product, we need to be careful, because the scaling coefficients will become conjugate. I would suggest you to prove this as a simple exercise. Simply get this linear combination and apply the conjugate symmetry axiom. Notice how axioms can be flexible. We just changed one axiom. The fact is that different axioms can lead to different results, and that's fine. We can build different constructions using different versions of the axioms, and they can all be useful for specific things. In this case, with this version of the axioms that includes conjugate symmetry, the inner product is called the Hermitian inner product. An example of a Hermitian inner product is the following. The inner product between A and B is defined as the dot product between A and the complex conjugate of B. With this new definition, we satisfy all of the axioms, and we get a very satisfying norm for all vectors. Consider a general vector v equals vx x hat plus vy y hat. Using this Hermitian inner product, we can now calculate the norm of the vector v. That's it. So the norm is given by the square root of the sum of the squares of the absolute complex magnitude of each component. This is nice. It looks similar to some kind of Pythagoras' theorem, and it will always give us a real and positive quantity. It seems a very reasonable definition of a length. This nice Hermitian inner product will be the one we use from now on, whenever we have complex vectors. If the vectors are real, this Hermitian inner product becomes the usual dot product. Let's do examples. Let's recalculate the norm of the vectors we saw earlier using this new Hermitian inner product. We now need to add the complex conjugate here, which reverses the sign of the imaginary parts. So the first vector gets a length that is not 0, and it's a real number. What about the second vector? Let's calculate its norm using the new Hermitian inner product. So we have to do the complex conjugation here, which reverses the sign of the imaginary parts. And again, we get a non-zero real length. So we see that we get nice, logically pleasant results. All thanks to this small complex conjugation. Let's look at some more important properties of the inner product. When an inner product follows these axioms, including the positive definiteness one, we can then prove the following important inequalities. Schwarz inequality. This states that the complex magnitude of an inner product is always smaller than or equal to the product of the norms of the two vectors. Please be careful with the notation. Remember that in general the inner product of A and B is a complex number. This is why in this inequality we are taking the complex amplitude of the inner product, which is indicated here by the single vertical lines. Then, in the right-hand side, the norm of vectors A and B is written using double vertical lines. We use double lines to distinguish it from the complex amplitude. This inequality is nice to prove, and we can do so in problem classes. But now think about how this inequality applies to the usual dot product in real geometrical space. The dot product between A and B is the magnitude of A times the magnitude of B times the cosine of their angle. And since the cosine term ranges between -1 and 1, this confirms Schwarz inequality in this particular case. A different but equivalent way of showing the inequality is by squaring both sides, like this. Remember that the inner product of a vector with itself is equal to the norm square. Next we have the triangle inequality. The norm of the vector A plus B is always smaller than or equal to the sum of the norms of A and B. In real geometrical space, this is an obvious statement. It is telling us that a straight line is always the shortest path between 2 points. Next, we are going to see a final useful recipe to calculate the inner product of two vectors. The recipe is extremely easy when the vectors are written in terms of an orthonormal basis. So, assume an orthonormal base is being used. Vectors A and B are a linear combination of the basis vectors, as usual. Now take the inner product between A and B. Therefore, we have proved from first principles that the inner product of A and B is the multiplication of the corresponding components, conjugating the ones of the second vector. We have also proven how to calculate the modulus of a vector by doing the inner product with itself. We can substitute it to the recipe above and we get the following. Now remember that a complex number times its conjugate is equal to its absolute value squared. This is a property of complex numbers. So we can write these two useful results in a neat way. When applying these two rules to the usual three-dimensional real vectors, they become the familiar formulas for the dot product and the norm of a vector. Incredible, isn't it? We have proven the equation of the dot product and the equation for the length of a vector from first principles, just by assuming that the basis being used was orthonormal. But be very careful. We regularly think of the dot product and the norm of a vector directly as if they were defined by these equations. But this way of calculating them is only true if we are using an orthonormal basis. For example, in a previous lesson we saw a vector v which we wrote in the xy orthonormal basis as 2, 3. The length of this vector squared can be calculated directly from its xy representation by doing 2 squared plus 3 squared, because the xy basis is orthonormal. However, in a new basis E1, E2, which is not orthonormal, for example this one, the vector is given as 1 minus 2. The length of the vector is not 1 squared plus minus 2 squared, because E1 and E2 are not orthonormal. However, if we choose any other orthonormal basis, such as the one we saw earlier, Then the vector written in terms of its components is like this. And its length squared is indeed given as the sum of the squares of the two components. The length of a vector is a property of the vector, and therefore it is independent of the basis being used. If we want to use the familiar formula of adding the squares of the components, we have to remember that this formula works only if the basis is orthonormal. The amazing thing to realize is that these two recipes work not only in our usual real two-dimensional or three-dimensional vector spaces, but they work in any arbitrary vector space and using any possible orthonormal basis that we want. We can always compute the inner product using the components of an orthonormal basis in this way. So, if this is clear, we now know everything I wanted to teach you about the inner product. But to end the lecture, I would like to add a note on notation. This note is not something to study or do problems with. It's just that I don't want you to open a book in maths or physics in the near future and be confused when you notice that some inner products are reversed. This is because two different notations are regularly used. Let's look at them. To understand the two notations, we have to review the axioms for inner products. We had three. Conjugate symmetry was one, positive definiteness was another, and the linearity axiom was a third one. The linearity axiom says that the inner product is linear in its first argument. Now, combining axioms 1 and 3, it can be logically deduced that the inner product must be conjugate linear in the second argument, as we said earlier. So, if we do a linear combination in the second vector, the result is a linear combination of the individual inner products, but with the linear scalar coefficients being complex conjugated. This is easier to understand by considering the common example of the Hermitian inner product as the dot product between A and the complex conjugate of B. Clearly, if we scale B by a complex number, the whole product will be scaled by its complex conjugate. However, many books and lecturers, especially in physics, prefer to define the inner product in a different way, with linearity in the second argument rather than in the first. Then, by combining axioms 1 and 3, we find that the inner product must be conjugate linear in the first argument. So basically the same as before, but the other way around. In this case, the inner product would be defined as the dot product of the conjugate of A times B. Whether one wants the first or second argument to be linear is a matter of choice, as long as we are consistent. One just needs to make an arbitrary decision and stick with it. In my lectures, I am using the first version. In any case, don't worry about this. It is obvious how to translate from one notation to the other. Let's represent the first inner product with a subscript 1 and the second one with a subscript 2. To convert one into the other, we simply swap the order of the vectors. Many people, especially in quantum mechanics, use a different notation for the version that is linear in the second argument, using a vertical bar instead of a comma. So that's it for this lecture. Thank you very much for watching it.